Hello, everybody. I want to talk to you about statistics terminology today. So let me just jump right into that, and we'll get started. Where is my? There it is. Okay. So I've got this. This is available in the module as well. This is the thing you can download. I'm kind of just going to go through this and talk about some of the terms in a slightly different way than it's written here, but I'll let you read it as well, obviously. So statistics is basically the study of using incomplete information plus math to generalize about some group of something, some group of people or objects or animals or whatever, basically. And it's that incomplete information bit that throws people off a lot of the time because there's always uncertainty involved in statistics because you never have complete information. You've always got, you're never you're never looking at the whole population and measuring them or whatever, surveying them. What you're doing instead is using a subset of that population, we call it sample, we'll get to in a second, to generalize to the population. And we can be pretty precise doing that, but not 100% precise. There are always margins of error and uncertainties and whatnot in statistics. Don't take that to mean that statistics is unreliable. The margins of error are small and the uncertainties are unlikely if you take a good enough and large enough sample. So yeah, let's look at some basic terms. Before we can really do that, we need to have a language we can use to talk about those things so that we don't have to use vague or unclear terms. So let's talk about the basic terms of statistical analysis that we're going to be using. So variable is whatever thing you're studying. So if I wanted to know how tall American men are, then my variable would be height. The population is the group that you are trying to generalize to. So in my previous example, the population would be American men. The sample is the group that you are actually measuring. So if we, let's say, measured 50 American men, how tall they were, then that would be my sample, would be the people I actually got information from. And then parameter and statistic are they're nicely named. I don't know if this was intentional or not, but parameters go with the population and statistics go with the sample. They're both numbers about those respective things. So a parameter is just a number about the population. A statistic is a number about the sample. Now, those sound very similar, and they sort of are, but there's a huge difference that will become clear later when we start doing more advanced analysis, which is that parameters don't change. They're fixed. So the population is some group, we're thinking of it as an unchanging group of objects or people or whatever. It does technically change, but very slowly, usually. And parameters are numbers about those things, like the average height of an American man, right? That is some fixed number that doesn't change quickly over time. On the other hand, a statistic pertains to a sample, so it matters what sample you took, right? If I was measuring the height of 50 men, it wouldn't matter which 50 American men I chose, right? And if I took a different sample of 50 other American men, I would get a different average. And I would get different heights for the men. So statistics change based on the sample that you take. Parameters are fixed, that fixed things that were generally what we're trying to estimate using the sample. All right, and then there's two other things regarding samples. Sample size is how many people, things, etc., are in your sample, which is pretty easy to get confused with the sample itself. But what is your sample is a question about what or who, whereas what is your sample size is a question about how many things are in your sample. So it's what or who versus how many. A representative sample is the thing that you are always striving for as a researcher. A representative sample is one that does a good job of representing the population, which is why it's called that. You usually do this via randomness, which we might talk a little bit more about when we get the chance. But what you're really looking for is a subset of the population that is like the population but writ small. and then you analyze that small subset and generalize it to the large population. That is hard to do. This is actually the hardest thing to get in all of statistics. Computers are powerful. They will do lots of analysis for you. People have been working on statistics since the 1500s, sort of. And we have a good understanding of how to do all the math. The thing that we don't actually know, well, there are a lot of guidelines that you won't encounter in this class. This class is not about gathering samples. It's about doing analysis. We have guidelines for gathering good representative samples, but it's not perfect. And in fact, is one of the hardest things to do in all of statistics. In fact, you might, if you follow politics, you might be aware that polling in the last couple of presidential elections has been a little hit or miss. And there's a bunch of reasons for that, but the number one reason is that it is incredibly hard to get a representative sample of likely voters. I won't go into too much detail there. If you're interested in it, I'll be happy to recommend some articles, but it's very, very difficult to just call up a bunch of people and find out how they're going to vote beforehand. Doesn't work very well. Well, I mean, it works somewhat well. But yeah, getting good representative sample is just very difficult. If you don't, it's probably because it was biased in some way, and we will talk about bias in a little bit near the end of this video. Okay, so one thing I should say, for our analyses, we will generally be assuming that we have a representative sample, which is often not a great assumption, but we're going to do it anyway, because that we're not concentrated on how to gather samples, but how to analyze things once you have gathered them. So we're just going to assume that the gathering part went pretty well most of the time, and then we can analyze. So yeah, that's this course. We're not going to talk too much about how to gather representative samples, but if you are interested at all in statistics in the wider world, that's the number one thing you want to concentrate on. Okay. So there's some different variable types, and these are super, super important. At least the first two are incredibly important for knowing how to do analysis. So there's two types of variables: categorical, also called qualitative, and numerical, also called quantitative. I am used to using the terms qualitative and quantitative, and you will probably hear me do that a few times, not necessarily in this video because I'm being careful, but over the course of the semester, I guarantee I will slip up and call them the other names. I like categorical and numerical better because they sound more different, and people get confused by the similarity of the words qualitative and quantitative. Categorical, which is qualitative, just means a variable that falls into any number of categories. The most common one by far is something with two categories, like you ask a question that's yes or no. Do you approve of how President Biden is handling the pull out of Afghanistan, right? Answer is yes or no. You do or don't. And that's the most common categorical variable, but other things apply, like what breed is your dog, or what color are your eyes? Those things are the answers to those questions fall into a variety of categories and are not numbers. That's the important thing. They're not themselves numbers. That does not mean that we won't have numbers associated with categorical variables, but the numbers will be what percentage fell into each category, right? The answer to the question itself is not a number. We derive numbers from them by like how many fell into each category. Numerical or quantitative variables are ones where the answer is a number. So for instance, how far did that long jumper go? That's a number. How fast did you, or how long did it take you to drive to work today, right? That's a number. Those things are called quantitative or numerical variables. There's one very minor caveat here, which doesn't come up much, but I'll say it anyway. If the number that you're using is just a label, it's not a numerical variable. It's a categorical one. So the classic example here is phone numbers. You can't do math with phone numbers, right? You can't add two phone numbers together and expect to get anything that means something. Phone numbers are categorical, right? Those are just labels. Jersey numbers in sports, right? You don't add two jersey numbers to mean anything. Anytime you're using a number that's just a label, that's a categorical variable, not a numerical one. The test is, can you do math? And generally the math that you want to do is subtract or divide. And we'll talk about those in a little bit. There's this third one here, a lurking variable. This is not a kind of variable that you are studying. It is in fact specifically the kind of variable that you're not studying, but might have an effect on the outcome of your test. So lurking variables are bad. They are a common cause of misidentified statistical analysis, in the sense that, so a lurking variable is anything that might cause the outcome you are seeing in your study, but is not a thing that you're actually studying. So here's an example of a classic lurking variable. You may have heard this story before. In New York City, ice cream sales and murder rate go up at the same time. When ice cream sales increase, the murder rate increases, and vice versa. When the murder rate increases, ice cream sales increase. There's a bunch of theories that you could propose. Maybe everybody got brain freeze and got mad and started killing each other. That's not it. Maybe there were a bunch of murders and people needed ice cream to help them decompress. No, that's not it either. There's a lurking variable here, and the lurking variable is that it's hot. When it gets hot and humid in New York City, it is apparently miserable. I've never been, but this is what I'm told. It is apparently miserable, and people kill each other more in those circumstances. They have shorter tempers, and you get more murders. And also, they eat ice cream more. So both of those things are caused by something else, which is a lurking variable. There is not actually a connection between ice cream eating and murders, or rather, there is, but it's the fact that they're both caused by something else, which is a lurking variable. And if you just looked at ice cream rate and murder rate, you would be tempted to draw a connection between the two, or say that one caused the other, when it doesn't exist. Right? That cause is not one of those two things. There is a lurking variable there. So watch out for lurking variables. They're super, super, super important. If you're trying to draw any kind of analysis. Anytime you hear that a study has controlled for a variable, this is what they mean. They're trying to conduct the study in such a way as to take out a particular lurking variable. All right, that's what I want to say about that. I have a little thing here. I guess I will mention this. The distinction between categorical variables and numerical variables is super important. I'm going to tell you about some other ones in just a second, or some subcategories, but don't get confused. Categorical versus numerical is the thing you want to concentrate on, because how we analyze categorical variables and how we analyze numerical variables is completely different. And so before you do any kind of analysis, the first thing you have to do is say, okay, what kind of variable do I have? And that will tell you the kind of analysis you want to do. So one way that I like to be able to tell them apart is by visualization. I like to visualize myself asking some member of the sample the relevant question. So, excuse me, Mr. or Mrs. Giraffe, do you have any children? Or, excuse me, Mr. Toaster, how long does it take you to toast a piece of sourdough bread? And yeah, I know that's ridiculous. And honestly, the ridiculousness makes it more memorable. So yeah, that's why I do that. And if the toaster would answer with a number, I take 2 minutes to toast a piece of sourdough bread, then that would be a numerical variable. And if the giraffe would answer with a category, no, I don't have any children, that would be a categorical variable. So basically, if the answer would be a number, then it's numerical, and if not, then it's categorical. That's usually the way I like to think of it. And just a little imagination tip. Your brain works better if you have very specific things to visualize. I say visualize, but most people will just say the words themselves. Actually visualize, like picture yourself talking to a giraffe. You're in the savannah. There's a giraffe. It's really tall. It's leaning down to talk to you. What are you wearing? I'm wearing a white button-up shirt with a black tie. I have glasses and a green visor on. I've got a clipboard that I'm writing on. Like, have a full visualization. It actually makes it more realistic and more memorable. And I know that sounds stupid, but it's still an effective thing to do. Okay. So a couple of subcategories of variables. These are things that I am required to teach you, but I don't think are important, and they won't be on the test. But here they are. Variables. So an ordinal variable is a categorical variable with some properties of numbers. One specific property of numbers, which is that you can put them in order. So the best example of this that I know of are letter grades, A, B, C, D, F. right? So those are letters, they are labels, they're categories that people fall into, but you can put them in order, right? A is better than B, which is better than C, etc. You can't do math with that stuff directly, right? If I do A minus C, I don't get anything meaningful. Now, ordinal variables often come from numerical variables, like for instance, the percentage in the class, or your total percentage in the class, or your total points in the class. Those are numbers, and you could actually subtract those and do math with them, and it all makes sense. But once you categorize them, it's not they're not numbers anymore, and you can't do math directly with this stuff, but you can put it in order. So that's an ordinal variable. There are others. Categories of hurricanes is another one. Nothing else springs to mind immediately, but anything like that. And then there are two subcategories of numerical, well, there's actually more, but there are two levels of numerical variable, one of which is not important and one of which is. So the not important one is interval. Interval variables are ones where subtraction makes sense, but division doesn't. So something like, so in all of my time doing stats, the only two examples I've ever seen are time and temperature. Technically, any variable that has a scale that includes 0, but the 0 doesn't actually mean absence of everything. So for instance, 0 Fahrenheit does not mean the temperature is literally 0, like that there's no heat activity in whatever object you're looking at. It's just a point on the scale. Same thing with time if you're going by o'clock. So if I say our meeting tonight is at 6 o'clock versus our meeting tonight is at 8 o'clock. 8 o'clock is not like 1 1/3 more than 6 o'clock. It's like dividing 8 o'clock by 6 o'clock doesn't make any sense. Here are my caveats to those and why I say this isn't that important. If you use Kelvin, temperature's ratio, the 0 actually does mean 0. And if you're timing things, like let's say the women's 100-meter dash, right? So Elaine Thompson just ran a really good time in the women's 100-meter dash. She ran a 10.54. And Shelly Ann Fraser-Price came in second in that race, and she ran a 10.73. The 10 point, like you can subtract those times, that's usually what you do, but you could also find a ratio of them, right? If I divided 10.5 or 10.73 over 10.54, I would find the average rate, I would find the ratio of the average rate of speed that the two women traveled over the race, and it would make perfect sense. So yeah, if you're timing things, then the ratio works fine. And if you were using Kelvin, then temperature works fine. And I don't actually know of any other examples of variables that are interval but not ratio. So ratio variable is one where you can subtract or divide, and it makes perfect sense. So not only does the difference between two things matter, but the ratio of them also could potentially matter. It will make sense if you divide it. We'll return to these more when we actually do some statistical analysis. Yeah, there you go. Those are some subcategories of numerical variables, or of categorical and numerical variables. So these subcategories of numerical variables actually are a little bit more important. Discrete versus continuous. We'll talk about these more in topics 4 and 5. Is it 4 and 5? I think it's 4 and 5, where we have it's 5 and 6. Sorry, it's 5 and 6. I forgot I put another topic in there, where we're making a distinction between discrete and continuous. But basically, a discrete variable is one where the answer can only be certain numbers, which is almost always integers. Discrete variables almost always come up when you're counting stuff. So for instance, let's say my question is how many people are in the room. That is going to be 1 or 2 or 3, but it's not going to be 5 3/4. Whereas continuous is anything in a range, right? How much water is in that water bottle? Well, it could be anything between 0 and whatever 20 ounces is in the water bottle. Like literally anything in there, including fractions, are fine. So in general, if you are asking how many, that's discrete. If you're asking how much, that's probably continuous. Be a little careful with that wording, but it's a pretty good rule of thumb. And then here are some common statistics we're going to be using. Mean, we're going to use this one a lot. Mean means the same as average. They are synonyms. There's literally no difference. If you read in your book, the OpenStax book that we're using as a reference guide, they make some sort of arbitrary distinction about centers and centers of places versus numbers. Totally irrelevant. 100% irrelevant. Mean and average are synonyms to mean the same thing. There's a third thing in statistics that has the same meaning, which is expected value. We will eventually use those. We'll eventually use expected value as well. But mean, average, and expected value are all the same. The way you find averages is exactly how you are familiar with finding averages. You add up everything and divide by how many things there were. We will talk a little bit more about doing that slightly differently in the future, but that's the basic idea. Mean is usually used, well, it has to be used on numerical variables. You can't use it on categorical variables because categorical variables you can't do math with them, right? That's the specific defining characteristic of them, so you couldn't find their average. Proportions don't mean exactly the same thing here, or same thing in statistics that they do in algebra. In algebra, a proportion is like an equation that has two fractions, and that's not what we're doing here. For us, a proportion is the fraction of a categorical variable that falls into a particular category. So you could say percentage just as well, and that would be just fine. Yeah, but that's all proportions are. So we usually will use that variable to analyze categorical data. It is theoretically possible to use it to analyze numerical data, but we won't do that. And the median is another semi-common statistic that we use. We'll talk about this more in topic 3 when we talk about quantitative variables and displaying them. But the median is the middle number. Like if you take all of your data, so it has to be on numerical data. You take all of your data, you put it in order, and then whatever number's in the middle is the median. We'll talk about this more later. All right, I want to talk about sampling types and some biases, which are actually the most interesting part of this topic. So sampling types are not that interesting. There are many more sampling types in this, but these are kind of 3 major ones. The big one is the simple random sample. This is what is used basically all the time. A simple random sample is a sample in which every member of the population is equally likely to be chosen for your sample. That's not quite true. It's technically that every subset of equal size in the population is equally likely to be chosen if you're choosing a subset of that size. But it's just easier to think about one person at a time. So, or one element of the population at a time. So if you've got your whole population is some large group, and then that you're trying to generalize to, within that population, if it is equally likely for you to choose any member of the population to be in your sample, then you've got a simple random sample. This is the gold standard of sampling. With an exception, which is the next type, which is a stratified random sample. So a lot of the time, your population might have some subgroups in it that you want to learn about. So my example here on the sheet is that, let's say I was doing some work for a newspaper trade association, and I want to know how much time people spend reading newspapers. Well, if I just ask, if I throw the whole group of people into one big pot and select within that pot, we're going to get weird results depending on, a variety of things. But one of the major things that it would be depending on is the age of the participants in our sample, right? If we go to a college dorm room or a college dorm building and ask everybody in there how much time they spend reading newspapers, the answer is basically going to be 0. But if we go to a retirement community and ask people there how much time they spend reading newspapers, the answer might be, a couple hours a day. And so, like the subcategory of ages, I would break my sample down by ages in this case, would be really important, right? I don't want to lump in all the age groups in one big pot. I want to do them separately. And so I make what are called strata, and which are in this case delineated by age, right? I would take kids and like young adults and middle-aged and older adults, and maybe sample them separately, and then either stick all my data together at the end or break it out by subgroup or maybe both, right? And so that's a stratified sample. And then within each of the strata, I try to gather a simple random sample. So it's basically a bunch of simple random samples for each subgroup in your population, or it's one simple random sample for each subgroup, and you have a bunch of subgroups. That's what a stratified random sample is. The groups are called strata, like the crust of the earth, right? That you got your crust and your mantle and your core and whatever. I'm not a geologist, but those are called strata of the earth, and it's the same thing here. As you're breaking down one large thing into a bunch of smaller groups. Systematic sample. We're not really going to worry about this, but it is a thing I'm supposed to teach you. So a systematic sample is a sample where you like randomly order your population and then choose every nth one, like every third one or every 10th one or every 1000th one that is from your list. It is a way to generate a good sample. It's not technically a simple random sample, but we don't have to worry about why. I don't want to say too much about this. We're not going to do this. And then a convenience sample. This one's really important. This is not a real sampling type, or rather it is, but it shouldn't be. A convenience sample is a sample that is gathered out of convenience. Like for instance, if I was learning about newspapers and I went to a college dorm and just asked everybody in the dorm how much time they spent reading newspapers, that is a terrible sample. Like I didn't do any kind of randomization or try to get a representative sample of the population overall in any way. But it was very convenient because all the people were in the same place. And so convenience samples are generally riddled with bias, which we'll talk about in a second. So convenience samples are basically a bad sample that is bad because the researcher was lazy, essentially, and didn't do a good job of gathering a sample. They don't necessarily have to be lazy. They might unknowingly have, they might have omitted a variable and the sample was a convenience sample because of that. But basically, a convenience sample is a sample that is badly gathered out of convenience for the person doing the gathering. All right, so bias, and I think bias is the last thing we're talking about. Yeah, I got bias is the last thing we're talking about. So bias, a lot of people think of bias as like prejudice. In America, we often think of racism or ageism or ableism or all, any other kind of, or sexism, I guess is a really common one. Some kind of thing that, like, some views that a person holds that are, bad. They've prejudged a group, essentially. That's not the kind of bias I'm talking about here. The kind of bias I'm talking about here is anything that causes your sample to systematically under or over count your results, not necessarily count, under or over measure your results, makes your results systematically too high or too low or off in some way. It is near impossible to avoid all bias. It is basically impossible, in fact, to avoid all bias. It's really important to minimize it, though, because if you don't, you get a bad sample, and you don't want a bad sample because then you can't generalize your results to the population. So that's what bias is. It is anything that causes your sample to be systematically too high or too low or wrong in some consistent direction. So there are tons of kinds of bias, most of which are broken down in the last kind called sampling or selection bias. The first two I want to talk about are non-response bias and response bias, which sounds like, wait, I'm getting bias in non-response cases and also in response cases? And the answer is yes. Yes, both can happen. So non-response bias is the kind you get when members of your intended sample don't respond to you. This is super common in polling, for instance. Modern polling is usually done by people calling up someone else on the phone and asking them questions, right? That's really common. It's also common to have it to get it over the internet, which we'll talk more about response bias. But non-response bias is probably the most common kind in modern polling. The response rates on phone polls, which are the most common kind in politics, is under 1%. Like less than 1% of people will answer a survey. If someone calls up and says, hey, I'm doing a political survey, do you have a few minutes? Almost everyone says no and hangs up. And that means that if the people who are saying no and hanging up are qualitatively different in some significant way than the people who are answering surveys, then you get a biased sample, right? Your sample is biased towards the type of person who will answer a phone survey and against the type of person who won't. And those people are similar and different in complicated ways, but like they're different in some qualitative way. And so, oh, excuse me, my computer's losing charge here. I gotta plug it in. They're different in some important qualitative ways, and so you end up with samples that are not that representative. So that's what non-response bias is. It's when people don't respond to your survey, and it causes your sample to be non-representative in some way. Response bias, on the other hand, is when people do respond, but give you answers that aren't true. And the first thing you're probably thinking of is, why would someone lie to, take time to do a poll and lie to the pollster? It's not that they're lying so much, it's that often people don't know what is true about themselves. So let me give you a really good example of this. In 1982, the 1982 California governor's race was a race between two people, Tom Bradley, the governor of LA, and George Deukmejian, who I don't remember what he did. Deukmejian eventually won. So all the polls leading up to the governor's race had Tom Bradley ahead, pretty significantly, 7 or 8 points, something like that. And then on election day, Deukmejian won, and Tom Bradley didn't win. And there were, why? All the polls had said Bradley was going to win. Why would this happen? Well, it turns out that when all the subcategories were broken out into their own groups, white voters didn't vote for Tom Bradley as often as they had said they would. And Tom Bradley was black, or is black. I don't know if he's still alive. And Deukmejian's white. And so there was a theory that white people said to the pollster that they would be willing to vote for Tom Bradley, when in fact they were less comfortable voting for a black person than they said they were. And a lot of them ended up changing their minds and voting for Deukmejian instead. It's actually called the Bradley effect, by the way, named after Tom Bradley for this reason. There are theories about there are other theories about why this happened, but that's the most commonly accepted one, is that people said to other people a thing that they thought was what they should say, even if it wasn't what they really believed. This is technically called social desirability bias, but that is a category of response bias, of which there are several. I had another example in here, right? Oh, yeah. A famous poll, I believe in the 1980s, also asked two of the same question, but different ways. So one of the questions was, should the government spend more on welfare? And one of the questions was, should the government spend more on helping the poor? And people who got the welfare question overwhelmingly said no. 60+% said no, we should not spend more on welfare. And people who got the help the poor question overwhelmingly said yes. Over 60% said yes, we should help the poor. The thing is, that's what welfare is. Welfare is just government programs for helping the poor. So those are the same question. But how you phrase it, because the Republican Party basically poisoned the word welfare so much, people were sort of primed to say welfare bad, and no, we shouldn't do more welfare. But people are actually, in their hearts, compassionate and wanted the government to do more to help poor people. And so basically just the wording changed the response by an incredible margin. Like, this is the difference between, a 35% yes and 65% yes is massive. Something that is 65% popular is tremendously popular. And something that is 35% popular is quite unpopular in general. A lot of your questions fall right around the 50% mark, with conservatives saying one thing and liberals saying another thing. And so to go like well into the yes majority or well into the no minority is quite a big deal, especially for two of the same question. So those are a couple of ways you can get response bias. How you word the question, and maybe what the question is about. People don't always know, and they're not always willing to say what their preferences actually are. So the most common kinds of response bias show up when the question is really sensitive, or when it's really polarizing or divisive. So you can get a lot of response bias that way. But response bias is when the answers that you get aren't true from the people that you're surveying. And the last kind I want to talk about is a huge kind of bias, sampling bias. There's way too many kinds of these to go into. There's, I don't even know how many subcategories. I have a list of like 15 of them. But basically anything that causes you to gather a bad sample is some kind of sampling bias, causes your researcher to gather a bad sample. The most common kind of cause of this is a convenience sample. You take a sample that's convenient to get, and that's probably not going to be representative of the population in general. So for instance, I'll give you a good example of, so I used to have projects that people could do to gain extra credit, but extra credit doesn't work in this class because we're using master grading. So we're not doing that this semester. But one of the things that people have studied, that my students have studied in the past, is how much time people spend studying for their classes. That's just one of the projects they were doing. And they would try to survey people. And so for instance, they might stand outside of the library or go into the library and ask the students there, how much time do you spend per week studying for classes? That is going to have sampling bias in it. That's a convenience sample for sure. The reason it's going to have sampling bias, so for instance, is that this is going to estimate everything much too high, probably, because if you're going to the library, that's where people who study a lot go. And so you're not going to be getting a good cross-section of the population. You're going to be specifically talking to people who study a lot, and so your answers are going to be too big. And that's a kind of sampling bias. There's all kinds here. I listed 3 kinds in here. Yeah, survivorship bias, self-selection bias. So survivorship bias is there's some sort of weeding out process, and so you end up taking your survey only after that process has taken place, and so you end up getting a sample that's not representative of the broader population, but only the population of survivors. So one really good example of this is you might see like a book by a CEO of some company saying like, their autobiography, or like how I made it, like what I did to become successful. That's a classic example of survivorship bias, because the only ones who get the books are the ones who became successful, and it has nothing to do with the ones who didn't become successful, right? You're like someone who tried to be a CEO but never got very far and only ended up in middle management. They don't get a book deal. And so what you get is you get a bunch of people saying, here's how I made it, and trying to find patterns among those people is actually not very effective, because they are usually more alike in some ways. Like people who become CEOs usually had a wealthy upbringing. And so, but that's not most of the population. If your question is, how do I become a CEO? Right, having a wealthy upbringing won't necessarily do much for you, even if all the people who did, even if all the people you read about did have that upbringing, because that's not necessarily your experience, and it's not the experience of most of the population. So, even most people who have a wealthy upbringing don't end up becoming CEOs. So that's an example of survivorship bias. There's another classic example about shooting down planes that if you ask me about, I'll tell you about. Self-selection bias, people who can self-select into a survey, for instance, will generally all have some similar characteristics. Like if you ever see the pop-up ads on YouTube or wherever you are, wherever you're on the internet saying, take our poll, right? Do you approve of President Biden or whatever? Those are self-selected. Like everybody who clicked, you have to take a proactive step, which is to say to click on the ad to do it. And all the people who click on the ad probably have some characteristics in common. Like, yeah. And so you end up getting a biased sample that way too. As you can see, it is very, very hard to get a non-biased sample. It is, like I said, up here, representative sample is essentially the holy grail of statistics. If you can get a representative sample, you can easily generalize whatever results you get from the sample to the population. And of course, that's very hard, as it turns out. So yeah, getting a representative sample is tough. There are all kinds of bias, and we're not going to go into them in much detail. This is basically all the time we're going to talk about them, except for thinking about it when we see problems throughout the semester. But we're not going to like go into great detail about how to avoid this stuff. That's not this class. This class is all about mathematical analysis. So we're going to concentrate on math, assume there wasn't any bias in the sample, et cetera, et cetera. So, but these are the main kinds: non-response, response, and sampling bias. All right, and with that, I feel like I've been rambling on for a while now. I'm going to go ahead and stop the video here. Let me stop sharing. Yeah, and I will see you guys in the next video.